Alright, let's do a practical calorimetry problem here, particularly to college students. We're going to boil water, which is a complicated cooking procedure. So what we've got is a pot full of 1 kilogram of water there at 20 degrees Celsius. We know the heat capacity of water. We're going to put it on a burner, on a stove, and the burner's output is 2 kilowatts. So the power coming out of the burner is 2 kilowatts. I want to find how long this is going to take, because I'm hungry. So let's do this. It's a little bit different than your average calorimetry problem, but the fact that I have that heat capacity there pretty much begs me to use this equation in some way. Right, this equation is what allows you to figure out how much energy it will take to heat something up across a certain temperature range. And I said we're starting at 20 degrees Celsius and we're bringing it to a boil. So of course that means that the final temperature is 100 degrees Celsius. So we know M, we know C, we know delta T, right? So we can go ahead and calculate the energy that will go into the water, right? This QW. So we know how much energy it's going to take to bring this water to a boil. All right. But the other, it's not like we're dropping a hot object into cold water. We're heating it up, and we know the power output from the stove. And we'll assume that, we'll simplify things and say that all of the energy from the burner goes into the water. Now really it probably wouldn't, right? It kind of heats the air up and everything, but let's say all of the energy from the burner actually goes into the water. So that means that this energy required to heat up the water, well, that comes from the burner. So I could also say that the energy from the stove is equal to MW/CW delta T, because that's where the heat's coming from. But we don't know the heat from the stove. We don't know the heat energy. We do know the power of the stove. And remember that power is the transference of energy over time. And Q, that's just energy. So we can say that the power of the stove is equal to the energy of the stove over the time. Or if we rearrange this, the heat energy of the stove is equal to its power output times how long it's on for. So I could write that here. Okay, and solve. Okay, so that's how long it's going to take. We know all those values. I think I'm going to actually plug numbers in because I tried to pick realistic values, and we'll see. And I'm getting a time of like 16 seconds. I wish I had this stove, so that's not good, right? It takes longer than that. It could be because the really not 100% of the heat does not go into the water, right? Or I could have just picked poor values, but so there you have it. This is the way with better numbers that you can determine how to figure out how long it's going to take to boil your water so you can have your ramen noodles. Yep. And interesting other fact is that the heat capacity of salt water is slightly lower. The more salt you add, the lower the heat capacity is, and that means it takes less energy to boil it, which means it takes less time to boil it. So if you're cooking something salty anyways and you're impatient like me, just put the salt in right away and it'll boil faster. So that's your physics cooking advice. All right.